Okay, this is I just want to welcome you to Chemi 340 again. What I wanted to do is, let me see, I need to make sure I know how to switch back and forth. I'm actually on site at the Penn State wastewater treatment plant. For those of you that have sort of never been here before, I got permission today, thanks to John, I was saying Joe Swiderski. Wanted to thank them. Note that today is Earth Day, and so I usually like to talk about global cycles. We touched a little bit on biofuels last time, really the focus there tends to be on carbon. Of course, the emphasis is not only on the fuel itself, but also on the global warming as well. There are some issues that are not as popularized, I should say, that have to do with other cycles, and nitrogen and phosphorus are two of them. I do know that, you know, there's certainly a lot of you that may be motivated, shall we say, to be, or hoping, shall we say, to go into saving the world through pharmaceuticals and so forth, and certainly the COVID circumstance has made that sort of more prevalent. But I think one of the things that people don't appreciate is the whole reason why we have the opportunity to be afraid of COVID is largely because things like advances in wastewater treatment have actually saved far more lives than the entire pharmaceutical industry combined. And so understanding, you know, that we have this largely under control is something that is not tended to be appreciated. And I hope you can gain some understanding here about that. And it's not all about health. It's also about energy. And to kind of put that in perspective, I visit wastewater treatment plants whenever I get a chance, cities all over. The last one that I was on a tour on was down in Philly. And in the description of that facility, the guy was saying that upwards of 1/3 of the energy used by the city of Philadelphia was in the water-based system, and the majority of that was in wastewater treatment. So you have to think about the energy usage associated with treating water is comparable or on the same order of magnitude as running the entire city. And as we go through this, it's going to be an interesting thing here today because all of you are gone. It turns out that the wastewater treatment facility doesn't have enough, for a better, we'll go with a 4-letter word, poop here. Doesn't have enough poop to run the place. It doesn't have enough energy input in the biological material. And so as I go through here, I'm going to mention some things, but what we're going to start with, and I want you to understand is, we can discuss this kind of like an electrical plant. It's all about, just like every biological process, reducing and oxidizing things. The whole goal of wastewater treatment is to oxidize everything. If you take things and you oxidize the carbon, then it goes off into the atmosphere and becomes CO2. Here, that's a good thing because it's not leaving as a hazardous material. If we oxidize nitrogen into things like nitrates, we'll end up with fertilizer. Same with phosphorus materials or organic phosphates becoming, organics becoming phosphates, phosphorus to phosphate. They become fertilizer. And inherently, if you think about it, because we're working with human waste here, human waste, of course, would have a lot of problems with human pathogens. And that's why we focus so much and really solved this problem in health in the world, which really started in many ways about the time of World War I. So the activated sludge process I'm going to describe here is from that era. And we'll talk about that as we go. So let me go ahead and switch the camera here. And let me start out by pointing out, as we head into the primary aeration basins here, that this facility is really designed for about 3 million gallons of water a day. And right now it's running at about 500,000. Million sounds like a lot, and it is. And so the process has to be very well designed to really control two different retention times. You want the solids to stay behind, the water to run through as quick as you can and get clean. Because there's not enough biological oxygen demand or poop, it turns out they're actually feeding it. They're actually spending right now a lot of money buying carbon. This is called micro C, which is basically an alcohol-based system. So they're feeding, if you will, energy into this system to keep the microorganisms alive. Because if you don't have the microorganisms alive, they will you'll lose control of the process. Ironically, because the cost of this is now is quite high, actually, they just figured out that they could get the waste from the airport because they use alcohol-based de-icing, and that alcohol de-icing will actually is a waste product they pay to get rid of. And so now the university waste system is picking up that for free, and now they don't have to do that. And they're literally feeding it into the tank to keep the organisms alive. Now you can imagine at the front end of a wastewater treatment plant, up there you have to get out the bits and the pieces and the grit and so forth, and that's what the filters are. And this is just a primary aeration tank. Now, because there's such a low BOD, they're just kind of holding, they're holding steady, shall we say. They're minimizing the amount of feed into the system and just kind of keeping things running, and a lot of the things aren't actually running here. When you go from this primary aeration tank, you go to a secondary one over here, which is full. It's kind of a neat opportunity here because the others are empty. And this is a settling tank. And the whole goal here is to settle things out, which if you look down inside this area here, these are pretty deep, and as it settles to the bottom, you see these big chains, and they're just dragging the sludge down into the pits over here and getting the solids out of the system. So this efficient system that's called the activated sludge process was actually developed in early 1900s, when they made the observation of, by throwing a lot of aeration into a primary tank and then literally recirculating that, they thought they were activating the sludge kind of like you do activated charcoal. They didn't know what the process was, and it turns out it's just really facilitating very rapid growth and collection of the bacteria with a bunch of protozoa, a bunch of eukaryotic critters that may flocculate together and stick together, and then that gets them very activated for the process of consuming the carbon and so forth that's coming into the system. And so by having a highly activated recycle, you can think of it a recycle-based stream, what you end up with is organisms that are raring to go and also easily settle, because you're trying to always get the water separated from the solids. So the amount of construction right now, because they want to make it a little more self-contained, a little less using the materials that came from the university and the surrounding community, and so they're separated now. So the university is planning to handle, shall we say, its own poop and not the community, and that gives them a little more control, except on, say, football games. So that primary tank here, now just to take a real global look at what's going on here, the sludge heads down to the tanks you see down here, and those are anaerobic. You see they have sealed tops on them, and so those are biogas generators. And so within those tanks, what you would be doing is taking that sludge, undergoing very inefficient respiration, if you will, so that you retain a lot of the energy, and then the waste product of the electrons is methane. So you're basically taking the carbon, sticking 4 hydrogens on it, and creating methane, and then it phase separates. And so that's an anaerobic digester. So, you know, from here, aerobic, and the process right now goes down to the tanks that are down here, where you have aeration basins, and those aeration basins actually are trying to oxidize everything they can. So if we now think about, you know, the big electron balance that you know, we'll call it the world and so forth. You know, the sun is here, okay, and the sun has a lot of energy to shake loose electrons. We talked a lot about that, and grow plants, and that helps them to reduce carbon. But plants have that fundamental difficulty in getting the highly the nitrogen from the air, and that's because the enzymes associated with that are inhibited by oxygen. And as a result of that, there's an awful lot of this process of trying to do biological control is based on controlling oxygen levels. We'll talk about that a little more down in the aeration tank, and then there's other tanks over in there that are the anoxic tanks. But controlling the electron flow that happens in these things is all about that. So remember that really in the global nitrogen balance, we can thank or hate the Haber process for creating the agricultural revolution that has allowed us to reduce nitrogen from air. We're standing in 79% nitrogen, right? But we can't use that biologically unless we burn methane. So that burning of the methane, ironically, pointing here at a methane generation tank, that methane burning then gives enough energy to reduce the N2 in air. Remember that N2 in air has that triple bond, and that's why it's so hard to break that. And reduce that to then a usable form for fertilizer. We then eat that material, and then that comes here to the wastewater treatment plant. We're going to walk our way on down here to see a few other things that are here. This was a very complicated wastewater treatment plant, and the construction that you see here is actually a new technologies they're putting in for both removal of phosphorus by having, these will be tanks in here designed to be at a certain aeration and redox to allow for organisms to capture the phosphorus. And on the backside, it's going to be over in here, is where they're going to have membrane filtration. So they're going to go to a membrane-based technology for the final purification. Somewhat ironically, this wastewater treatment plant, unlike most, doesn't have a restriction on the effluent associated with phosphorus, for example. And the reason is that the effluent from this is actually pumped all the way several miles up to Tough Trees area, where they spray it out onto fields. And even in wooded areas too there. And so since that phosphorus is basically going into a giant biological filter and not going into the local streams, they don't have a restriction on the phosphorus. But nonetheless, they are developing the technology for the removal here as well. Now, these basins that we're sitting here, get it out of the wind. This is actually a kind of like the old school first generations of the activated sludge process. And so the center tank, so just a little while ago, it was up and rolling, but now it's a little bit of aeration and so forth going on in there. The center is where they would actually aerate and activate the sludge. Then it would come over into the secondary area here, which is more still. And if you look closely on the outside, you'll see these metal weirs here. And so the clarified water that then would actually spill out into this outer tray. And so this was actually sort of a self-contained activated sludge process where you could, for a small university, small at the time, or community, you could have a self-contained sort of 3-compartment aeration system where you have compressed air up and running, and from that going into these systems. These are actually all going to be demolished because they'll be replaced by the new technologies that you see over there. Where a lot of the energy goes, or should I say comes from, or is burned in a wastewater treatment plant, is compressing air. You have to blow a lot of air into these systems to overcome the, to provide the mass transfer. We've been talking about mass transfer all the time, KLA and so forth, but those mass transfer coefficients are to try to make money. Here, you're trying to get rid of waste, so you want to minimize the amount of energy that you put in the power to achieve the oxidation that you are. A little building on the side in front of us here is actually chlorination, because this little self-contained area where I am right now was the original kind of activated sludge wastewater treatment process. So as we walk sort of down through here, what we will be seeing is a little closer look at the methane generation or biogas generation, where the retention time in these is weeks. So remember, you're doing all that solid separation and to get the sludge, and then that sludge, the excess activated sludge, that's not recycled back to the aeration basins, is actually put in here, and it digests under anaerobic conditions to produce methane. Now, for a tiny little facility like this, it turns out that you can't generate a lot of energy. And in fact, if you look back behind us here, there's a flare that is sometimes burning, okay? Since there's no students here and there's not enough energy, not enough poop coming this way, that flare is not burning right now. But that's in a small thing like this. But for a large plant like the one in Philly, they had a dozen 10 megawatt Jenbacher generators where they actually designed the engines to convert the methane into electrical power. And so a lot of a large wastewater treatment facility, what they'll do is they'll purposely then try to create their own energy. And for a facility like, if you've read the chapter that was assigned last week about the wastewater treatment facility up in Boston, it's one of the largest in the world. That facility is running, I think it was 3 million gallon digesters like this. Even then, they still don't have net energy production, but they were working on a project to allow food waste to be purposely now, what's inside this building, it's not open at the moment, but what used to be here was a project that I worked with Jack McWhirter. He's a big supporter of our department, actually. Made his money in student housing here after being and we did a project here on autothermal digestion. Now, what's inside here now is a press. And so that press is actually, like, think about having two things of bands of really strong cloth between rollers, and the rollers then kind of impinge on each other, and so you put all the stuff in there, and then it kind of squeezes out the water, and then that material normally is what then is watered enough that you would then send to this landfill. One of the other big costs of wastewater treatment is because of this issue of working with let's see, we'll get you back here. Because I'm going to, because you're working then with human waste, you have to be concerned all the time about the human pathogens. We did a project, okay, so that material actually goes to a hazardous landfill. In fact, this material from this area in central PA was going the whole way down near Philadelphia. There are not that many hazardous landfills, and that's quite expensive. The alternative was to try to use the energy in the biomass. Remember that poop's got a lot of energy in it. Would it be possible to use the energy in that to generate enough thermal energy that thermal energy can be used to bring it up to pasteurization? Remember that sterilization requires you to boil a lot of water and get hot for a long period of time. Pasteurization only requires you to get to about 65 degrees Celsius. And if you can hold it there for 3 hours, those 3 hours, that's called pasteurization. That's considered a no longer human pathogens that can live in there. And so if I can take then the sludge from, remember, it's coming to the anaerobic digester. We're trying to extract a lot of the electrons there into methane, okay? And then we take it over to the filter press over here. At that point, the energy that's still in it, if you could actually heat it up, it becomes fertilizer. And in fact, that particular process called autothermal aerobic digestion is being used commercially in some places, even Tacoma. It's so successful, the amount of fertilizer they're producing, that they are getting other wastewater treatment plants to send them their poop because they're actually making money on fertilization. A little wind here, and I hope you. But where I wanted to go down to here is the aeration tank. So this is where the primary oxidation of materials takes place. And so you can think of this as the big bioreactor. Now, one thing you'll notice here is that we don't, in this particular, that's a agitation, mechanical agitation. Now, I've actually done validation tests for impeller-based surface aerators, and I'll put together some pictures for this lecture there, but that are designed to be in million-gallon tanks. And so this is all about oxidation, getting the oxygen in as much as you can. And if you take a look here, okay, let's see, I want to drop my phone. I hope you're seeing that and not me. What's under here are sparges, okay? And so this is the same as the next to it here. And these tanks here, they're actually polymer sparges because they need to be using sintered metal like our your mammalian cell culture things. And in fact, because they're made out of plastic, they don't want them to be exposed to them. And so the whole reason that they had these submerged, and a lot of things submerged in here, is they don't want degradation of the plastic due to the solar energy, since they're normally underneath well, the other thing is that you want to think about this as a logical reactor system, because so little bio load right now provided by the university due to the shutdown. So look at that, you might be able to, the solid. You can see how it's aggregated and it would sediment. That's because it's activated sludge. But they were the organisms they want to be here for the process of removal. And so the control system that you have here that they're doing is that they found the solution. I talked to the plant guy today to add aerated on demand tank that you see in front of you. It's the same aeration oxygen demand here that they've literally shut them off here, and they're simply pumping it over into the other side then for that. Okay, so that's the basis then of the other of the control variation. Now, there's one more really important thing that I wanted to do, because what I wanted to do, this isn't really EarthDay until you think about the global nitrogen cycle here, which to me is probably one of the most kind of horrifying aspects of the energy use that we use for our current unsustainable society, and that is to remember that the nitrogen that's coming to this facility is coming to us from the Haber process. So we're burning large amounts of methane in air to get enough electrons. And now we don't want this nitrogen to end up into Chesapeake Bay. And so we have to get rid of it. And one of the ways that you can prevent loss of the nitrogen from being in the water is to turn it back into N2 gas. The Animox process, you can see it's kicking up. The dissolved oxygen must have gone low in this system. And so right now, instead of just simply drawing the oxygen from the tank here, they've actually turned on the spargers in this basin. And now you can kind of see just how much gas holdup. You'll see the whole level of the liquid has now increased, and we're dramatically increasing the oxygen transfer rates inside this process for oxidation. Now, getting back to what I was saying, think about the energy balance of human consumption of an agriculture. We take N2, gas from air, we burn it with methane, create a lot of carbon dioxide, and then we take that material, make fertilizer out of it to grow things, and then we add more energy into it in order to turn it back to N2 gas so it doesn't end up in our streams. And so we're paying for this in multiple times, if you will, the actual energy that, in fact, there's a process that one of the students had worked on installing up for the Hudson Bay in near New York City, where they actually bring in train loads or tanker cars from trains every day of methanol to dump into the final stages of the wastewater process so that they can use the energy of the methanol to turn the nitrogen compounds, the fertilizer, if you will, back into N2 gas, so that we can now burn more methane to turn it back into fertilization. So the concept then of trying to circumvent that is if we could actually use the energy to autothermally turn that, pasteurize that, instead we could recycle it. And then the last concept that I want to leave you with here today is a concept of the big picture of agriculture. You can see a big, they've really kicked this thing on. The big chunks must be coming up off the bottom. And so the process then, or let's say, think of this very simply. How much of the nitrogen that we make for fertilizer ends up in a wastewater treatment plant like this? But the reality is that an awful lot of our fertilizer goes into crops in the field, and then there's runoff. And so an awful lot of the nitrogen balance doesn't come here, because in a concentrated environment like a wastewater treatment plant, we have the ability to develop these technologies that allow us to prevent this from going out and being pollution, if you will. But if you think about a diffuse thing like a farm, that's not the case. And in fact, when you produce milk, for example, the manure is then collected. Sometimes you get a little bit of anaerobic digestion like this, but usually not. Instead, they throw it out in their field. And so okay, I think I've covered most of what I had intended to here. And so I did have some notes. Let me see if I did. I covered the autothermal digestion, the hazardous waste, the phosphorus, like I had mentioned before. I'm going to switch you back to the other mode here as we head out of the tank. As I mentioned, in most wastewater treatment plants, a major concern is the phosphorus, and this should be a huge concern. In the air, phosphorus is extremely limited and very concentrated. Places like guano is a big one. Phosphorus rocks that are present in the world built in the do phosphorus removal in wastewater treatment. I don't hope you don't have to use that safety life. You would actually add in chemicals like calcium lime. Lime is calcium hydroxide, and then that lime would have to react a lot with the carbon that was in the system before it could even get to the phosphorus. And so you'd make a bunch of limestone, calcium carbonate, and you'd also make a lot of then of the phosphate, calcium phosphate, and you would have a large quantities of precipitates that would be in there. And those precipitates would end up in your sludge and anaerobic digester and going to hazardous landfill. Okay, so there's iron-based, there's a lot of different things that were out there, but they were all based on precipitation. And the problem with precipitation as a technology is that you're basically throwing away the phosphorus, okay? Whereas this system that's being built in here is a biological, you actually, you grow the conditions of an organism that stores polyphosphates. Because there are organisms that, I mean, they'll suck up phosphorus as much as they can. They use a lot of energy to do that. And they make polyphosphates. You've heard of polyphosphates like ATP, right? TP, triphosphate. When you link together phosphorus, it has a lot of energy in it. And so under these circumstances, if you manage to come up with a means by which to concentrate in a biological way, there would be a way to then recycle the phosphates as opposed to simply landfilling them in other circumstances. And as I mentioned, this entire technology is going to be different. Where downstream, the final polish in this system is going to be actually based on microfiltration. And the filtration will actually then remove the materials. Okay, I'm going to switch back to, oh, that is me. These are actually obviously clarification tanks over here. Does anyone have any questions?
This might be like a little off, but what happens to hazardous waste material? Like, does it just stay in bins?
Yeah, that's a good question. A hazardous landfill, it's hard to get that certification. And you have to do things like put in, it has to be in the right geological location where we're hoping for the next 1,000 years that stuff doesn't leak out of it. It's not like a typical landfill. A typical landfill where a lot of biological material goes, that's where you get like gas generation. You know, if you've heard of landfill natural gas, it's because we put so much biological material, a lot of which is diapers, but we won't go there. You then generate methane from that, and you can recover the methane from that. Hazardous landfills, like the ones that they have special hauling, special permits you need, and the idea is that it has a clay liner in the bottom so that water doesn't leak out. When you fill up there forever, which and never happens. Other questions? Oh, I must have a question. Yeah, I can. Okay, so if we go back over here, okay, these two basins are the same. Are you looking at me or at the, I can't tell.
We see you right now.
Yeah, okay, you don't want to see me. Let me see how I can undo that. Okay, so these two basins are the same, okay? So this basin, if you can hear me now, this basin is the same as the one that's full, okay? What we have down there is a bunch of spargers. So this is an aerobic process, and a huge amount of compressed air is being blown into this tank through polymers, okay? Polymeric spargers, just because they're reasonably cheap, okay? And so I said that one of the reasons why they still have them covered with water and running here is that they don't want that polymer will actually degrade in sunlight. And so even though they're not full, they're keeping water on here and trying to protect them from the sun, so you don't get the degradation of the plastic that's occurring down there. Now, the other thing which I think I didn't mention, which I will now that you asked about polymers, is that over in the filter house over there, one of the characteristics you can imagine, if you try to filter something and it's not the right particle size, if it is small, it clogs filters, right? And what happens then is it clogs up and then you can't get the water through it anymore. And so industrially, what you do when you want to filter something with small particles in it is you add a flocculant that'll actually allow water to run through the mesh. And that's done with a cationic polyacrylamide, actually, for a lot of this type of things. And so it's for anyone that's in the molecular biology world, polyacrylamide's used a lot for gels for that, but this is a different, it's also called China Flock is a trade name. What it does is you add this in to the material, and then two things happen. Since it's a cationic polymer, it will actually absorb on that, because most biological cell walls and things like that are negatively charged. And so that cationic material will actually absorb onto that and make it fluffy. And then when I go to filter it, because it's now fluffy, it prevents it from blocking the filter, and the water will actually run through it. So probably in that building right over there, you see the truck and so forth, and you see big bins and stuff. A lot of that is likely to be cationic polyacrylamides that are used in the filter presses here on the final stage. So once you've sucked all the electrons you can out of here, where you first do it with aerobic, then you do it with anaerobic, and then the leftover sludge from there goes to the filter presses, okay? That is where you have a very small volume. Even for a facility this size, it is actually hard to find a filter press small enough that can't process, 5 million gallons of wastewater. That's how efficient filter presses are. And literally you'd be sending a couple trucks a week out to the hazardous landfill. There is a process where you do oxygen injection, for those who want to make a connection to KLA, that if you take that sludge and instead of doing anaerobic digestion, what you can do is you can actually put oxygen into it. We're not talking air, because if you put air in there, there's too much nitrogen and it strips off the thermal energy. If I actually do countercurrent processing, I can actually get enough heat that the process will get to a temperature that will pasteurize the material as well. And so those processes are actually done. And I guess I would be remiss if I didn't ask one more really important thing about the history of wastewater in our department, is that Jack McWhirter, the guy that had done the process here, he actually has some of the most successful wastewater patents ever. And the process is called a UNOx process. And it seemed crazy to many people at the time that it would make sense to inject oxygen into waste. Mass transfer is dependent on the driving force, and that you have 21% oxygen in air. If you inject oxygen in there, your mole fraction of oxygen goes up by 5 times, from 20%. And so you can get extremely high mass transfer rates that actually make the wastewater treatment process so much more efficient that it's actually cheaper to separate the air by cryogenics and inject oxygen into the system to do that. But they're not big enough. And so since they weren't big enough, what the UNOx wastewater treatment process did is that for the existing cement in the ground, you could basically process 5 times more, so that as communities started to grow, continue to grow, they didn't have to build more wastewater treatment facilities. They could use the ones they had and actually use the enhanced mass transfer of oxygen injection to allow them to use existing facilities without huge capital investment. I don't know how much money they are putting into this wastewater treatment plant, but it's going to come back fully operational. They just got the permits to do that actually next week. And he told me that there were 65 people from the companies on site doing this renovation, if you will, to the university's facility. And that'll be back up and running next week, or the construction will be. Any other questions? Very, shall we say, appropriate location for thinking about the nitrogen balance of the planet. And I just want to make sure that everybody remind you, this is Earth Day. You should do something. I've already started to turn my garden. And I'm going to go back now and make sure I get my onions in. They're way late this year, but you know, do something nice to the earth today, please.